Okay, so let's get started. The project so first of all, a few things about the semester. We're about the halfway mark right now. So it's 8th. It's somewhere in between last week and this week was the half semester, basically, because 15 lectures is what we have, and this is the 8th one, that was the 7th one. So the project proposals, which was supposed to be kind of due this week, I just shifted it to be after spring break, because that way at least you can completely destroy your spring break thinking about what project to do, and that makes me happy. So the other thing is temporal planning. I mean, I'll talk more about the projects in a bit, little bit more. Temporal planning homework is due on 18th March. Basically, it's about the stuff that we discussed last time as well as the stuff we're doing today, except it's sort of like almost writing a domain for temporal planning. Sort of thing. And then in terms of exams, people keep asking me about this. All I can say is the midterm is likely to happen starting 3/27 onwards. Okay, so at least I have told you this. And how many of you know unexpected hanging, the paradox? You know the unexpected hanging? So the paradox of unexpected hanging is this guy has been sentenced to hang to death, but then they come and tell him that next week you're going to be hung, but it would be a complete surprise. The day would be a complete surprise. So this being a mathematically, smart, too smart guy, he basically reasons the following way, that it can't be on Saturday, because if he hasn't been hung all the way until Friday, then clearly they can't hang him on Saturday, because that won't be a surprise, right? And so now by mathematical induction, you can then prove that it can't also be Friday, Tuesday, Friday, Thursday, Wednesday, Tuesday, Monday, Sunday. And so he assumes that he would not be hanged at all next week, and that is very happy. And then, unlike on Wednesday, he just gets hanged. And he's extremely surprised. So it's exactly what they said. So the point I'm saying is that I'd like to have it sometime basically on 3/27, because that gives enough of a time after the midterm, and there's a couple of weeks, etc., and the last 2 weeks during the midterm. But I reserve the right to kind of shift it a bit. Okay, it can't be shifted earlier. I know there are people from India where we have this concept called preponing. We won't do preponement, we'll only do postponement, if at all. But so that's the thing. And for the final, if there is a final, the university mandated final exam time is May 4th, 2:30 to 4:20 p.m. and it is in Kurn 199. It's not in this room. Remember that. I wrote this on the schedule, so just remember. Again, whether or not we'll have final depends on other things, but if there is a final, it will be on that particular time. And you basically, and you should assume that that time would be used somehow by me, because I've been promised a certain number of contact hours, and I must contact you during those days, and that would be one of them. So if there is, what we do during that time remains to be seen, but that's the time for the final exam. Okay, so that's about the things. Any other questions on the exams? Yes?
I have one about the proposals.
Yeah, that I'll be talking about next one, more, okay? So for the topics coming up in the rest of the semester, normally this is, if you've taken enough grad courses, you know that this is the halfway point when the professor says, you guys can teach yourselves. So you kind of present each other papers, and we relax and enjoy. And unfortunately, I just can't do that. I mean, if you want to teach, you get yourself a class. You take my class, you get to visit with me. Part of it is because I believe that, as it will become clear in the next slide, actually understanding something and teaching it to other people is much harder than just saying, I read the damn paper. Okay, and And the biggest worry for me is people randomly reading a paper and wasting other people's time by standing in front of them. You don't understand, it's okay, it's your life, that's true, okay? But why must everybody else be suffering? Well, you don't mind suffering because you suffer for them, they suffer for you, the entire class is happy. But the reality is, please understand that if you can teach yourself, then they don't have to pay me for teaching. Seriously, not that they pay me for teaching at all, I told you we get paid only for research, but seriously speaking, but honestly, if to understand something at a level where you have a perspective about it, it requires some, proficiency in the area, right? And so I'm not a big believer in, basically students teaching themselves, because mostly I don't want them to waste other people's time. If there's any time to be wasted, I would like to do it, so that I wasted time. Okay. Anyway, so the topics, there will be wall-to-wall topics coming up, all the lectures will be used. We are going to be doing some more temporal planning today, and then maybe, depending on how we get done, we will shift into hierarchy and abstraction, which is actually another very interesting thing. Planning, basically, you don't do planning in the small action by action level, you do it in bigger tasks, and then make sense of what happens. And of course, there are all sorts of interesting questions. Everybody loves abstraction, but nobody knows where they come from and what sort of properties they should have. And so we will talk about that too. Then maybe partial observability, which is basically if there's uncertainty if you don't know the initial state, then this incompletely specified initial state, how do you still do planning? That's the bomb in the toilet problem, remember. Then we'll actually get into, at some point of time, we'll get into stochastic planning, which is basically connected to partial observability too, because you can think of partial observability as uncertainty in the observation, essentially. So there we'll talk about reinforcement learning. How many of you actually have done reinforcement learning in Intro to AI? Okay. Yeah, see, one of these things is, unfortunately, I realize this is the problem. This is why I said everybody should have taken Intro to AI at the level I teach it to take this class. But there is so much I can do, because of which we keep saying the same one lecture reinforcement learning every time. So you never get to the next level. So what I'm probably likely to do is, since you are supposed to know reinforcement learning, I will make the reinforcement learning as I teach in the Intro to AI class basically prerequisites. You make up for it yourself, and then I will assume that you understood that and do more, further, additional topics on RL. Especially, for example, things like policy gradient have become more interesting because of their connections to the way LLMs are being, trained and so on. So we'll do that. Okay. But honestly, you do need to know what is a Markov decision process. You need to understand reinforcement learning from a Markov decision process perspective. You can take the lectures that I have recorded for 471. That would give you a very good idea, at least, as the way I would expect you to understand it. So you should make up for that by that time you get there. Okay. Again, as I said, we can restart everything. We can start multiplication too in this class, but there's only so much you can do if you start restart everything. Okay, so that's some of the topics coming up. So in terms of the trimester projects, I wanted to say a little bit more, and then if there are questions, you can ask me too. So type 1 projects is do something project. So basically, you have an idea. This could be, for example, take an existing paper and algorithm and extend it. Okay, and then having done that, you write a report about what you have done. Okay, or run the code of an existing paper on additional benchmarks. Having done that, you write the paper. Doing this is normally a great way of understanding how research is done in terms of baby steps, basically. Because if you're writing an actual project or writing a paper, then you have, for example, how much time are you going to work on the experiments? How much time are you giving yourself to writing the paper? This time management issue, etc., becomes very important. And of course, doing the stuff that you're doing, is it interesting or not, is really what becomes, is it significant, is it interesting, are the kinds of things that, if you submit a paper to a conference, that's what they care about. In fact, in research, the problem is however hard the idea is, if it's been done once, then it's done. right? So for example, you cannot any longer write a paper about how to develop nuclear bombs. It's extremely hard to develop nuclear bombs. Not that I'm telling you to do that, but you can't do it. It's extremely hard to do it, right? But writing one paper, nobody cares because it's understood. One of the things about science that you have to understand, unfortunately, is if one person in the humanity understands it, it's done. Right? And for the science to progress, one person in the humanity should understand, and one more person should understand what this other person has done. And then so that they can, if this guy dies, this person dies, that other person can carry on other things. That's it. The rest of us can actually relax and enjoy the show. Okay. So to some extent, that's the significance part. The thing that in the class projects, we don't care as much about significance. It's okay to take somebody else's existing algorithm and either implement it or extend it. You can do one more, for example, benchmark on something that somebody, some particular paper that has looked at some benchmarks, and you might want to run it on a different benchmark, etc. Essentially, doing anything winds up taking all sorts of interesting detours, and that's the only way you'll figure out how to do these kinds of projects. Okay, that's type 1 project. Type 2 is understand something. Okay, basically you can, and the way we did it, truly speaking, actually, okay, where is the, I thought I put this, give me just 1 second. Yeah, okay. Yeah, so understanding something sometimes is harder than extending the state of the art in a small kernel. Please understand that. Okay, that's my thing, that writing a mediocre survey review paper may actually be easier than doing a mediocre original idea. But writing a really good perspective-oriented survey paper is much harder than doing an epsilon extension in some frontier of science. Okay, but all of you obviously know, even before ChatGPT, that survey papers are the way to go. That's because writing a mediocre survey paper is easy. Read a number of papers, start citing them, and then basically say some random, hierarchy or something of papers, and you're done. Right? One of the advantages is survey papers are exponential in number. Right? That is, if there are n papers, then you can write 2 power n survey papers. Right? Because each survey paper basically considers some subset of papers and writes some random things. Okay. The point I'm trying to say is it's both easy to do a bad survey paper and much harder to do a really good survey paper. And since I don't believe that people actually have the maturity to write very good understanding of a paper, etc., that's part of the reason I'm not letting you teach yourselves. If I believed it, I would let you teach yourselves, and I take off. So the point basically being that the second, let's go back. So the type 2 kind of project is take 2 papers, and we made it this way. Take 2 papers, make a presentation, video, record your presentation. And the way we did this is, again, you will read enough papers. There will be enough people that could have filled this whole class wall to wall, just like every other graduate class or several other graduate classes you probably might be doing, where half of the semester is spent listening to other clueless people like yourself talking about the papers they read. Okay, but what I plan to do is you understand, you record. The reason of the video recording is basically just because it's too damn easy to ask, to prompt, an LLM to generate a survey paper. At least I want you to talk. Of course, you can then spend time saying, I'll give the script to my head and then animate it. You can do that too. If you do that, yeah, fine, that's okay. You spend time on something at least. But more importantly, I'm not going to make anybody, the only way this will be evaluated, quote unquote, is the damage is limited because only the people who do type 2 projects would be asked to listen to other people's type 2 projects. Not all of them, but each of them will wind up listening to the YouTube presentations of 2 to 3 other type 2 projects, and then write some reviews. So that's basically like a separate section of people. And to some extent, as I was saying, this is probably what everybody would go for because this is somewhat harder to get because writing, as I was saying earlier, writing a mediocre survey paper is way easier than doing even a simple original one. Even though opposite is true for actually good survey papers and good original papers most of the time. Okay, so that's basically about type 2 thing. I think you can see what I'm saying, that basically you should aim for the type 1 if you can. And type 2 is mostly to give like a leeway to people who just don't have the maturity or the ability to pick up projects. Okay, so that's basically what the story is. Yes, there's a question? You said you had a question about?
Oh, sorry.
What?
So for the proposal for the type 1 project, like, what exactly is like the?
So what we will, basically we'll send a message. What we will wind up doing is you'll be putting your proposal on the piazza, but in a form only visible to the instructors. There's a way of posting such that it's only visible to the instructors, so that other people don't have, other people don't get to see your thing, and then that way we get to comment on it. Okay. In general, you give enough. If this one basically just lists the papers that you're planning to read. Okay, and for this one, you give as much detail as you can, essentially, so that we can give you, the more detail you give about what you're trying to do, the more criticism, critique you can provide. In general, if you're doing type 1 project, if it's something that is relevant, something that any of us can help with, you are welcome to use the office hours and also the piazza to ask for directions and suggestions, etc. But that's like more of an apprenticeship system because each project is different, right? And some of you will pick things that you are interested in. And in general, it's like whether is this relevant to this is judged sort of loosely, right? If you can somehow make a connection to something related to either planning or LLMs or anything that we've been talking about, it's all okay. Any other questions? Mm-hmm.
What's the final project for
You're not even taking the course. Why are you asking this question?
Well,
He's auditing. We should tell him that. Yeah, go ahead.
I'm going to do the type 1, so what's the final project for it? Or is it a paper?
It's a report, yes. And I think the way it would be done typically is type 1, in the past, we had type 1 project people present, short presentations about their paper in addition to the report. Because you did something, you get to present it. Okay. If you read other people's papers, it's like, I don't know, it's like I said, some people may really, really understand something. Honestly, understanding is harder, as I said, but most people just read at some level and write something. So, any other questions? Yeah.
For the proposal, do we actually have to show, for type 1, do we actually have to show some preliminary results or just what we
For now, just basically say what you're going to do, that's it. Because it's only, the whole thing is obviously highly compressed schedule. It's only 1.5 months you have. So you have to have, and again, it's basically people who are thinking about something already might very well focus on that, and then I can't stop it because I can't just sort of zero out your brain before you come into this class. So you may very well have been thinking about some project before, and then you decide to do that, and I can't stop that. That's completely fine. Okay. Yeah. Other questions? Yeah, in general, this is a reasonable, both of these involve, as I mentioned in the thing, both of these involve search, actually thinking about what sort of, there's like a humongous amount of things, and then, the big problem is this issue of deliberation scheduling. The more time you spend exploring, the less time you have actually to do the project. It is what I say. So that's sort of something that you try to learn in these sorts of things. But okay. And in general, the idea is honestly, if somebody were to do a really good type 1 project, really good one, right? Then pretty much the rest of their performance the rest of the semester doesn't really matter. So you can imagine the rest of the semester, the homeworks and the midterms, etc., are because I'm not convinced that all of you will do, all of you may be able to do very interesting type of projects. And so rather than, just make it all one way, then at least we can see what others do on the students. Okay. I think I made it very clear, right? Whether type 1 is what you should try if you can. It's like, would you rather have a Nobel Prize or a McDonald's hamburger? It's not a question, honestly. No, we don't go for Nobel Prize because it's too hard to get it. That's it. So then you convince yourself that hamburgers are just as good. And that's fine. Yeah. Anything else? But just because you took the type 2, don't make a bad version of it, because as I said, other people, at least 2 of your type 2 types people will be listening, 2 or 3 of them will be listening to your proposals and your presentation and see if they understood or not, and then write comments, etc. Anything else? Yeah?
So regarding the type 1 projects, is our extension of that paper or algorithm, does it have to be academically focused like it would be for research papers?
Any type. I don't know what does academically focused mean. If you re-implement some algorithm,
Okay.
right, and are basically if you take the code from the GitHub and then ran some more things, etc., that would still basically be in the spectrum of type 1 projects.
Okay, I see. So it could be more like application focused rather
It's
than-
completely fine. Yeah. There's no such thing as, I think, they're completely fine. That's not an issue. Application versus theory is not the issue. I mean, it's not like I'm saying type 1 projects must have theorems, for example. That's not true at all. Some people might have theorems, some people may not have theorems. Some people might just have empirical studies. Right? That's why I said, I mean, do something versus understand something. Yeah.
Other than report, are there any other deliverables like GitHub repo or something?
We basically, I think the report will have a GitHub repo, etc., so that if we feel that this whole thing was generated by, ChatGPT, then your grade also would be generated by ChatGPT. So, that's basically it. Okay. Yeah. Again, that's a sad part. I mean, we are in this world where science completely depends on trust. And the whole idea is science, I'm sure I probably said this once in the class, the whole idea is in science you only get to screw up once and then nobody pays attention to you. You just get to say, I did cold fusion once when you didn't do it. And then after that, you'll never be allowed anywhere near. Politics, on the other hand, of course, you can keep coming back, saying, I saw Jesus in the jail or something. Science, you just basically, once you lose trust, then you lost trust. But what is happening, unfortunately, is there are people who don't actually care about the science. And they're just doing it. They need papers right now just so that they can get jobs. That's it. And they don't expect to actually have a career at science, and so they don't mind if their name is completely damaged. Who cares? Right? That's part of the problem. So I hope that I'm not going to be able to police everything, but we just have to take it seriously. Anything else? Okay. Yeah, so we're going to talk about SAPA, which is the temporal planner that you read about also, and also, I guess that's SAPA, the actual terrace rice fields in apparently Vietnam. That's what I'm told. I've never been there, as I said. And I thought I'll show you some pictures of the people because there are 2 papers that we're talking about. Which one is this? Okay, these are all here. It's okay, fine. Let's leave it there. So this is Min's 2005 dissertation time, and he was taking that. And then last time when I was teaching this, he showed up, and he had like 3 kids. And in fact, one of his kids was actually going to ASU back in 25. So And these are the 4 people that wrote the required concurrency paper that you read. Of course, this guy with a lot of hair in the middle. Both of the guys with the hair have lost hair, but that's Dan Weld and that's Will Cushing. So you can see the guy with a lot of hair is now, this was 2 weeks back in India. That's Mawson. He has lost his hair. More dramatically, I would say, than me. And then that's Dan Weld and me in Sedona, like 2 years back. He's actually going to be here this weekend, next weekend, because he spends like a week every year in Sedona with his wife. He's in Seattle, but anyway. So I just thought I'd show you some pictures, and I told you about this. So let's talk about plan representations, and then go through what SAPA is doing, and also let's do something about the required concurrency stuff that you already read. If you have any questions, stop me. But a couple of things. So if you're thinking in terms of a temporal plan, one of the interesting things is temporal plans are actually the more interesting real-world plans. So an executable plan that must provide the actions that need to be done, and also the start times for each of the actions. It's not enough to say these are the actions that need to be done. You have to say when are these actions supposed to be started. And in fact, if you don't know the exact start time, one thing you can do is you can say that the start time of this action at the end time of this action has to come before the start time of this other action. That's just a precedence relation. And in general, if you have an action, you can basically, for each action, you can sort of think in terms of, if you have an action A, you can say A start, A end, are the time points. Right? And those time points are actual real numbers because they are on the metric in the actual time scale. Okay? So if I want to then say you have B, then it also B has B start and B end, then you can to actually say A precedes B. Right? What you just need to do is you need to say AE is before BS. End of A is before start of S. And an interesting thing is these are called the qualitative relations. So you just say AE before BS, and A should come before B. That's it. But in real world, sometimes there actually could be constraints on how soon before B should A come. How late before B can A come. So in general, what you really want to talk about is this, BS minus AE. This is a real number. Because these are 2 time numbers, right? They're real numbers. BS minus AE. And I can say L1 is less than or equal to BS minus AE less than or equal to L2. That basically says an interval into which these 2 time points, the difference between the 2 time points have to come. Do you understand what I'm saying? So this actually is, so if you are thinking about this, then AE before BS can actually be written as BS minus AE less than or equal to infinity, 0 less than or equal to BS minus AE less than or equal to infinity. Right? That's it. So basically, this is the more general representation because this actually allows you to talk about how much time can elapse between the 2 actions, one start point and end point. Okay, so one of the things is, as I said last time, we talked about interval algebra. Intervals will basically talk about the interval A, interval B. Intervals have start and end points, and then they can talk about during, in between, etc. And it turns out all the interval algebra constraints can ultimately be translated into actual constraints, called quantitative constraints on end and start points of the actions. And this should not be that hard for you to figure that out. Right? And one interesting thing, so this is basically what we are saying. So instead of saying A comes before if A1 comes before A2, I get to say A1 45 before A2. What that means is, assuming that basically actually these are no longer actions. Think in terms of points, time points. This could be the start point, end point of some action, and this could be the start point of another action. So these two time points, the difference is between 4 and 5. What actually that means is 4 less than or equal to start of A2 is, I actually wrote it down myself. So this is A1 the action and A2 the action. So I basically decided to kind of now talk about the start point of A2 minus start point of A1 less than or equal to 5. In general, actually, they basically just, there is a description called temporal network. There is a constraint satisfaction problem called temporal network. Okay, and a temporal network essentially no longer has durations. They just have points, time points. Okay, and you can talk about time points T1, T0, T2. Let's say you have, and then you get to say there is a constraint between T1 and T2. And like for example here, the constraint between T0 and T1, and that is given the direction. That means T1 less than T0, T1 minus T0 is less than or equal to 3, and 0 is less than or equal to that. That's what that constraint means. You see what I'm saying? So this is basically a constraint satisfaction problem. If you have a plan, normally a temporal plan typically is associated with a bunch of actions, some time points corresponding to the start times of the actions. Assuming that it's a simple fixed duration actions, then if you give the start point, then you know the end point, right? Because you just add the duration, you get the end point. You don't need to write both start and end of both of them. And then, just a second, and then you can basically write the constraints between these time points. And the constraints between the time points essentially are just like this. And one of the advantages of it this way is any assignment of real values to these times that is consistent with these constraints is a correct assignment. So then you get to talk about dispatching a plan. That means what you mean by dispatching essentially is that these actions have some restrictions, but the exact time at which those actions have to be started is left up to you within the constraints. There's infinite number of real numbers because time is a dense real field, right? Dispatching essentially is just saying, tell me time points during the execution. You don't get to say, it will happen sometime. You actually have to execute by starting. So when you execute, you actually know the time. You see what I'm saying? The times in which you are executing the actions should be consistent with the temporal network. There's a question.
In the previous slide, would it not be start of action 2 minus end?
Yeah, I think that's actually what I would say is I'll change this, but just assume that we basically, this is not well defined. A1, 4, 5, A2 is not well defined because am I talking about the end point or the start point? Right? We'll just assume these are time points. A1 and A2 are the time points. So the ST part just ignore. Okay? And I'll change that slide. Okay? And then, so basically, interesting thing about it is that now a plan is a set of actions and this constraint network. These constraint networks are generalization of the partial ordering, right? Because partial ordering in the normal classical planning, plan space planning, was A1 is before A2, A3 is before A5, etc. And so any order in which, any total order of that any topological sort of that ordering would be a valid execution sequence. Because there was no notion of time in classical planning. Now, doing action A1 coming before A2, how much before A2? If I do A1 now, can I do A2 like 10 years from now? or do I need to do it within 2 years? In fact, you know that real world is a lot more like that, right? For example, you you have some flexibility, but there are some constraints. You must, for example, complete your entire program in, normally in 2 years. I don't know whether you guys realize this, by the way, that like you join, let's say, bachelor's, it's 4 years, master's, it's 2 years, and PhD, it's 5 years. But university has extra rules saying master, like a bachelor's program, like at least I know for PhD. PhD cannot take more than 9 years. Cannot take more than 9 years. Which then nobody tells you, because none of you, if I even mention the number 9, you will just stop doing PhD. You say, are you crazy? Are you thinking it can take 9 years now? Okay, so basically, but there is this extra thing that, if you're taking more than 9 years, then essentially you have to get extra permissions, all that random stuff. So there's always constraints on, it's never like A is before B. It's A is before B, but the interval is defined. One of the beautiful things essentially is, so first of all, if you take those constraints, yeah, okay. And if you actually have something like T1 precedes T2, T1 precedes T3, and T0 precedes T1, let's say. This is just predecessor relationships, like from the classical planning. You can write them as a simple temporal network, right? Because you can start with T0, T1, T2, T3, right? And then I'll say T0, T1, T0 precedes T1, that means this is 0, infinity, right? And then T1, T2, because these things will always be 0 infinities. If you have just normal precedence relations, they'll all be 0 infinities, okay? And T1, T3, again 0 infinity. And then of course, normally if it's a real plan, then you will have to say T2 precedes TE, T3 precedes TE. Right? And then then you have a TE and right? So I just wrote the same thing in a different form. Now, if I understand, if you have a qualitative, quote unquote, precedence relation network like this, the only thing that matters is getting any topological sort is correct, right? Because the exact time doesn't matter anymore. You just need to get a topological sort. And you happen to know that topological sort is polynomial, right? So it's not surprising that this simple temporal network, this is actually a simple temporal network. You should ask what makes it simple. It's temporal network, what makes it simple? We'll get to that in a second, okay? This simple temporal network, right, happens to be such that finding, an assignment that satisfies all the constraints, which is basically a topological sort, can be done in polynomial. This CSP can be solved in polynomial. Okay. Now the interesting thing, what makes everything here is fine, right? 0, 3 is fine, 7, 20 is fine. This 1, 5, 7, 9, that's the problem child. So what this thing is saying is T2 minus T1 can either be in the interval 1 to 5 or in the interval 7 to 9. Do you understand what I'm saying? That's possible. That can be, in fact, I would argue that we always need a disjunction It's just that we threw the disjunction into the search space. So suppose you had action A1 was giving, condition C to action A2, and action A3 is deleting C. Right? And because these are instantaneous actions, they are points. Really what you needed to do is you just have to say A1 less than, you needed to just say A3 less than A1. Or A2 less than A3. Right? You just basically didn't see the disjunction because you threw the disjunction into the search space. Think of search space as a way of handling disjunction so that the nodes will be all the search nodes will be conjunctions of constraints, and any disjunction is pushed into the search space. That's how normal search is done. And this is an extremely important point, so much so that you should write it down somewhere, that normal search involves keeping search nodes to be conjunction of constraints with any disjunction thrown into the search space. This is actually a very deep point. It's actually a very deep point. And it comes up across the board. So if you want to, the question of course is conjunction of constraints. So you don't like to see disjunction on your face. But you can define terms, redefine terms. Imagine it turns out that you consider, say, capital A is either A1 or A2. Capital A, an abstract action A is either A1 or A2. And similarly, the abstract action B is either B1 or B2. And you want to put a constraint saying all the A's should be, any A's should come before any B's. If you normally write it this way, then in the search node you will have a constraint saying A1 or A2 precedes B1 or B2. And that doesn't look like a conjunction because they're actually disjunction in the constraints. But you just say, this is just A1, this is just A, this is just B. And you feel good. My taking flight action should come before taking Uber in the destination action. Taking flight action can correspond to 10 different actual planes. Taking Uber action in the destination can correspond to 100 different Uber cars, etc. So I abstract it out. Abstraction is least committed. This is another thing that actually will be coming up very soon. One way of thinking about abstraction is you don't want to commit to the details. If you don't want to commit to the details, you are actually allowing disjunction in the search space. Disjunction, the reason you people don't like disjunction is because computationally handling disjunction kills you. Computationally. So, just a second. So, you know what? The reason you can't do this, the reason you didn't do this in classical planning is you basically put these into two different search space branches. One with A1 before A2 and the other one A2 before A3. But by doing this, you committed prematurely to one ordering over another ordering because you have to do search. What if it turns out, unbeknownst to you, that essentially one particular direction leads to a problem, and that problem might actually have happened in the other particular direction too, potentially. So you would fail multiple times. You rediscover the same failure multiple times. An idea would be to keep the constraints like this disjunctively and check if the set of constraints anytime becomes infeasible. You see what I mean? Just as you want normally given constraints, you want to check if the constraints are satisfied. But what's more interesting to you is if the constraints are not satisfiable, you get to backtrack. You guys understand what I'm saying? So you actually check whether the set of ordering constraints I have, is it still feasible? Fast order planners do this too, but they never allow disjunctive constraints in the middle. So checking cyclic, basically an ordering constraints become infeasible if there is a cycle. You see what I'm saying? But checking that if it is a conjunctive constraints is polynomial. Checking that if it is a disjunctive constraints is exponential. It's NP-hard. Actually, if you have these kinds of constraints in the constraint set, and you keep them, hold on to them, and if they ever become infeasible, you can kill the entire branch. Imagine if you ever did that. The other guy would have split this disjunction into different branches, would have basically failed in all these branches. You got to fail just once and got clean out of it. The reason you do abstraction is there is no point in figuring out. For example, if your flight is going to Dubai right now, right, there is no point in figuring out which flight in Dubai with which flight in which Uber in Bombay, because there are no flights in Dubai thanks to us right now. Right, there are no flights in Dubai. So if the abstract level, the actions are not there, then you might as well kill that plan. You see what I'm saying? Instead, you will try for one plan, one action, and then die, and then another action die, another action die. Instead, you die at a disjunctive level. To do this, you essentially have to keep this, least commitment means disjunction. I mean, if you have like two boyfriends or girlfriends, you can't make up your mind, you want to hold both of them along, that's disjunction. They say you are commitment phobic, but you say I'm just doing abstraction. You see what I'm saying? That's essentially what it is, ultimately. Search is faster that way. I mean, human relations may not survive that, but search is faster that way. Okay? But, okay, so the interesting question in doing this is there is a trade-off. There is a per node search node cost. So you have a trade-off between per node cost, processing cost, versus search space size. You put disjunction, you're reducing the search space. The best is, I'm not going to make any commitments. What are you going to be? I hold it to myself. I'll figure out which one will work eventually and decide that's what I want to do. When are you going to graduate? I will figure out. When are you going to get married? I will figure out. Everything is least commitment. The search space is just one node. Right? But are you done? You have no idea. Is it infeasible? Have you made commitments that are basically violating each other? It's much harder to check because you have all this disjunction. Do you understand what I'm saying? So disjunction reduces the search space size, but increases the per node processing cost. But there is no reason to believe that the extremes are going to be good. Somewhere in between can actually be good. Put some amount of disjunction and throw some into the search space can be better. Can be better than put everything into the search space versus put nothing into the search space. Okay? And so where we went, notice where we went from. We are still talking about temporal planning, but temporal planning is also connected to classical planning. If you have predecessor relationship, that's a constraint satisfaction problem. If you allow disjunctive constraints, If you allow disjunctive constraints, then disjunctive ordering constraints, checking whether a set of disjunctive ordering constraints is actually consistent is an NP-hard problem. Checking if a set of conjunctive constraints, that basically simple constraints, A1 is before A2 and A7 is before A9, etc., whether that set is consistent is fall under that one. And you know that one because topological sort is fall under. Try to do topological sort when you say A1 is either before A2 or before A5. Right? Or even worse, A1 is before A2 or A7 is before A5, one of them. This is all a long-winded way of telling you, first of all, two things. Remember repop that I mentioned? I think I mentioned this. Basically, this is using planning graph heuristics to improve efficiency of plan space planning. And there were two ideas that we used. I went too quickly on it, but if you really want to understand what happened there were two ideas we were using. One of which is implicit mutexes. That means if A is giving condition C to B, and and so like this, what I'm saying is, if A is giving condition C to A1 is giving condition C to A2, and A3 is deleting condition Q. A3 is giving Q rather. Condition Q. It looks as if there is nothing wrong with each other. But if in fact C and Q are mutex, then that's as good as saying C and not C. That was one of the ideas I mentioned. The other idea was in the report paper, what we did was we actually kept the constraints, the ordering constraints to be disjunctive. So if there is like a promotion or demotion to be done, I won't commit to that. I just actually write it as a disjunctive constraint, just like what I wrote there. Basically, it's not the end of the world. Again, NP-hard essentially means it's exponential, but you can have a polynomial time problem that takes longer because of the input size than the exponential type problem. Right? And it's not the end of the world, in fact, just because you have exponential time thing. And so we actually do that, and that's how repop actually does much better than normal classical plan space. And the second thing that is actually going into the abstraction part is I could also have avoided committing to the actions. Do you understand what I'm saying? So here, A1 is giving C to A2 and A3 is deleting C. I basically decided to write either A3 before A1 or A2 before A3 as a disjunctive constraint. But imagine a different scenario, a related scenario, where I need for B, I need the condition Q, and either A1 can give Q or A2 can give Q. Both of them can give Q. You don't know which one to pick. So your normal idea is to pick A1 in this branch, A2 in this branch. What if I tell you, pick both of them? A1 and A2 will give Q. One of them will give Q. We'll figure out who actually gives. That's a disjunctive action. Right? And so I can give a name to this now. I'll just say, hi, you want A1 and A2? I'll just call it A star. A star is either A1 or A2. And I'll say A star gives Q. So I put A star in. And then unbeknownst to you, I'll say, well, A star actually, my friend, cannot be done. A star is an abstract action. It cannot be done. It needs to be reduced to either A1 or A2. By the end, you need to pick which action. If you do this, this is a hierarchical planning. This is it. This is it. I mean, you can add some, the only difference between full-on hierarchical task network planning and this is here A is just being, the A is considered a non-primitive action. And it is basically, kind of reduced to one of either primitive action A1 or primitive action A2. In the general hierarchical task network planning, which I will not tell you right now, I'll get to it later, but basically what happens is you can have an A star and it can be essentially reduced into plan 1, plan 2, or plan 3. All these plans are partial plans with abstract as well as concrete actions. And these are called the reduction schemas. You see what I'm saying? And so now when you put A star, you are essentially saying, I have this or this or this. Disjunction over constraint sets, not disjunction over constraints. Disjunction over constraint sets. But you remember your friend, either De Moivre or De Morgan, the guy who allows you to distribute conjunction over disjunctions and disjunction over conjunctions. You can go back to that. So when you get to HTN planning, that is what you need to think about. We will get to it in when we come back to think. But that's basically the disjunction. And whether or not a set of constraints are satisfiable depends on what type of constraints they are. I mean, how hard is it to check if a set of constraints are satisfiable depends on the type of constraints. For the ordering constraint, simple ordering constraints are checkable in polynomial time. Disjunctive ones can be hard. For other kinds of constraints, actually complex constraints can actually be semi-decidable or even undecidable. This is what I'm saying. Okay, there was some question. And this is, it's like you opened a little bit and started thinking of, representing these kinds of, connections between time points, and all of a sudden, we can start talking about general, least commitment, general disjunction, and how that affects the trade-off between per node complexity versus search space. And if you say, tell me, Rao, which one should I do? No, there is no such thing. Figure out how to split the trade-off. You want to understand the essential trade-offs in the world and figure out how to, and assume that whenever there is a trade-off, for it to even be a trade-off, it can't be the case that the correct answer is one of the extremes. If the correct answer is one of the extremes, then why the heck are you talking about it as a trade-off? See what I'm saying? Like for example, sometimes like in terms of the cost matrix, people are trying to trade off the length of their airplane travel with the cost of the airplane travel. If there is no trade-off, if you always say it always should go for the cheap ticket, then there is no trade-off. That basically means even if it takes infinitely long, even if I'm selling you a ticket that goes directly through Dubai airport for tomorrow, and it's $1 less than anything else, you will buy it. Okay? It just takes infinite amount of time, that's okay. You see what I'm saying? A trade-off means it's not in the extremes. That's the whole point to understand. And you figure out the set of trade-offs and then see which bit you want to live. Yes?
How do you decide, how do you decide when to take a discussion in your project?
No, again, you just basically let me complete my sentence, and
No,
I think you're
have a
saying.
question, but if let's say that I'm a planning agent, right? And I'm trying to decide specifically, should I take this one or should I not take this one? Maybe, I've trained lots of models or something like that. How do
Again, there are certain times. By the way, since all of you want to understand every damn thing in LLMs, let me see the following thing. LLMs basically commit to a stupid token only if they think you are watching them. You say LLMs are next token prediction machines. They are not that. They are next token distribution prediction machines. A distribution is disjunctive. You see what I'm saying? And every distribution, and one of the other things, I probably already said this here, if not I said it in the talks that I recorded for you guys, that from an LLM perspective, a token is a point in the embedding space. There are infinite number of points in the embedding space. A finite number of them correspond to actual vocabulary items. The rest are all disjunctions over vocabulary items. They essentially can be thought of as some sort of distribution over the vocabulary items. this is connected also to the linear algebra idea of spanning vectors. You can have a three-dimensional space that has three important vectors, orthonormal vectors, and every other point in the three-dimensional space can be written as a convex combination of these three vectors. LLM thinks in terms of these points. It doesn't think in terms of cat, dog, etc. It thinks of this distribution, this other distribution, this other distribution. If it throws it at you, you say, what do I do? You have no idea what to do with the distribution. So it can actually be allowed to think in terms of the distributions as long as cognitively challenged people are not looking at it. And then when they're looking at it, then it needs to commit. Schrodinger's cat all over again. Do you understand what I'm saying? And it actually turns out that there is equivalent connections. Doing reasoning tokens in terms of latent space tokens, which don't necessarily have to correspond to single vocabulary items, can actually be more efficient. But when you have the user looking at you, you still have to tell them what you mean. So the point is, just because, again, even when you're doing abstraction, it's not like you ever get to say, my plan is A star, because that cannot be executed. When it's time to execute, you need to pick what reduction of A star are you going to do. The whole point is not make the decision prematurely. Make it when you are forced to make it. And in the end, of course, when you're about to execute, you are forced to make it. But sometimes you may be forced to make it because it may very well be the case that you're trying to do A star. It turns out that because of some constraints, A2 is not even possible. That means A star is really A1. That's basically what happens with disjunctive constraints. You're thinking it's A1 before A2 or A3 before A5. But then there is this another constraint saying A5 before, I'm sorry, let me write this down. You're thinking A1 before A5, A3, or A5 before A7. And then you just added a constraint saying A7 before A5. This and this basically cancel out, which means the only way this constraint can still live is if it becomes A1 less than A3. You guys see this? For those of you who took intro to AI, this would be unit resolution. Did you understand what I'm saying? Okay, so that's how basically the constraints here. So rather than decide which direction to go, you waited until somebody added A7 less than A5, and then say at that point, you actually are forced to make the choice, as against prematurely making the choice. This is the whole point of abstract planning. Why don't you pick your Uber in San Francisco right now? Even though you haven't actually taken the flight to San Francisco. That'd be a good idea. That's a premature commitment. Sometimes the Uber guy will give you extra $5 less. 10 days from now I need to be picked up at 10:43 from San Francisco airport. Because you're doing it ahead of the time and it's non-refundable, I'll give you $5 discount. If you're a bozo, you'll fall for that. If you have nothing else to do with your time, why not commit it beforehand? If on the other hand, you're one of these movers and shakers and lots of things are happening, then you would wait until you reach San Francisco airport before checking what Uber you're going to take. In fact, some of you are taking both Uber and Lyft at the same time and then canceling one at the last minute. Don't tell me that you don't do it. You are doing least commitment, my friends. And your choice is forced. Okay, Lyft came, so I'll take the Lyft, I'll cancel the Uber. You see what I'm saying? This is something that you do in life, and basically you are writing search algorithms which are doing it, and so if you make them do that too, that can be more efficient in certain ways. So the longer answer to your question is you wait until your choice is forced. If in fact everything is done and the choice is not forced, then you can pick any choice and you'll be fine. But when you are picking in the upfront, then you are more likely to be wrong. Do you understand what I'm saying? If the final plan contains A1 to AN in parallel, and each of them are giving P1 to Pn to the goal state, and there are no interactions, this is the final plan. Then at that point you ask what is the ordering between A1 to AN, yeah, it doesn't matter, pick a permutation, it will work. And factorial permutations, any one of those permutations will work. The problem would be picking which is coming before which upfront without any good reason. Any other questions? Yes?
Is there some kind of trigger that forces us to pick that action at that point?
That's what I'm saying. This is one of those things, because again, to understand some of this stuff, my friends, you need to understand some classical techniques. And a lot of you probably think LLMs are just working in vacuum, but really they are using classical techniques as verifiers and compiling the thing into the generator. Okay, that's what I said in the second lecture, and that's basically in the LLM second lecture. So somebody knows what is right or wrong. Okay, so one of the ways you do this is basically when you have constraints, there is a whole notion of constraint propagation. So, for example, in this scenario, let's see. Yeah. So anyway, so constraint propagation is an example of constraint propagation is this. So because it's like if you have A or B is a constraint, and not B is another constraint, you get A. That's called unit resolution. What? Oh, the software update, that's right. Yeah. Okay, that's basically how things happen. Part of the reason I'm saying all this stuff is you have to ask yourself how much of this is being done versus how much of this you say Hail Mary LLM or Hail LLM. You just do it. This is why I hope some of you will actually call LLMs are dumb temporal planners as a dumb paper. Check, and maybe they're great temporal paper. But the point is, the people who are taking this class are likely to actually know the difference between required concurrency and actually plans with interactions, etc., compared to the people who made tau bench, which have actions that don't have interactions. And so things work there, and then you put your, whatever, the open cloud on your own, the email server, and it eats up the entire email. And today there was somebody else who basically said 3 years of the database has been removed. So I just tweeted saying, like LLM-backed agentic systems in non-ergodic environments, what can go wrong? You're hoping that it's not that if you close your eyes and speed, you will every day get into accident. But you are definitely tempting the fate. Right? And when the accident occurs, unless it is Grand Theft Auto, repairing you is going to be quite costly. It could be infinitely costly. Right? So that's the reason of robustness. Anyway, so the disjunctive constraints, when the simple temporal networks have this kind of a disjunction, then they become actually exponential. And a simple way of making that exponential thing to be polynomial is take this network and say there are two networks, one which has only one of the same copy but with just 1 5, and the other the same copy but only 7 9. And if you did this, you now have two simple temporal networks. But you don't get to write to your mom saying, Mom, I solved, I basically proved equal to everything. Right? Because you shifted the complexity from the per node cost into search space. And you don't get any awards for that. Okay? Okay. Now, going back, let's see. Yeah, let's see. So that's the plan representation, of course, and then No, you can talk about, that's why you have plans, have things like Gantt charts, etc., which tell you exactly when the timing, the starts, etc. But if it's a simple temporal network, you can't write it in the Gantt chart because they are precedence relations. And simple temporal network is a better, more flexible representation because you get to dispatch the actions at the right time. Because you have your plan and there are also other constraints. You can add more constraints as needed, as against you commit to yourself and say, I must do this at this particular point. Right? And then, so of course there are, in the temporal planning, you have achievement goals that basically involve making certain things true at a certain time point. And instead of saying steps, previously in classical planning, steps are also time points. Now, time points are basically the real first-class entities. The beginning and ending of the actions might be the time points, and you might say, I need this to be true at this time point. The time point doesn't have to be an absolute time. Remember that. It is a time variable. Do you guys see that? Right? Because these are not absolute numbers at all. This is a temporal variable. This is a temporal variable. This is a temporal variable. And they can take any real world, any real number values as long as those constraints are satisfied. Think of this really as something like a graph coloring problem. The only difference is in the graph coloring you're used to normal CSPs where variables have a discrete domain, a small number of values in the domain. Right? Here you have a dense set of values. This is one of those cases where you realize that just because it became infinite number of values doesn't necessarily mean that everything goes out the window. Simple temporal networks have basically variables with infinite number of values, and yet they're only polynomial type. See what I'm saying? Okay. So problem representation, basically you have actions and the goal at a certain time point, and then you can also have persist goals, which is saying a goal over a certain time interval. And this is not, shouldn't be surprising to you. This is interval preservation constraint versus, basically point truth constraint from the your refinement planning data. Okay. Now, one of the interesting things about temporal planning is all of a sudden there are so many different ways of talking about the quality of the plan. Right? In the classical planning, what are you going to do? You just basically say the number of actions. And if you then give some arbitrary numerical cost to the action, then you say least cost plan, where you add up the action costs. Right? Here, on the other hand, you can have actions which have cost, you can have time, the duration of time, and basically you can talk about things like make span from the beginning to the end of the plan execution, how long will it take? That's the make span. And I mentioned to you the Los Angeles 405 construction thing, where basically they put more and more resources such that they can get done faster so that they can get that bonus. Okay? And the slack, which is the difference between the deadline for a goal and the time by which the goal is achieved by the plan. Right? And the slack is negative, then it's called tardiness. That's a late penalty. And one of the interesting questions is you could also actually have reward with respect to a goal specified either in terms of as long as it's actually achieved before the deadline you get full points, otherwise you get 0 points, which is the simple way. Or you can say, it's sort of some kind of a thing where, basically if you do it before the deadline, you get the full points, but after that it sort of decays in some form. The reward decays, becoming 0, which is basically your life, right? Because homework, is a deadline, is there, then basically say we want to get extra 2 days, and then I'll say every 2 days, every 3 minutes is what, 5 points or something. At some point of time it becomes negative points. So you stop doing the homework. See what I'm saying? You know this. Basically, this is more like real world planning. It's just that you convince yourself classical planning is hard enough. Okay. So, and then of course cost is of course the sum of the costs of all actions, and it can be split into, even the costs can be split into different kinds of costs. You can talk about resource consumption. This plan consumes, so time is one resource and cost is another resource. But I can say cost itself is split into the gas cost and whatever some other the food cost and all that stuff. And if you assume that all of them can be combined into a single number, which is dollar number, then it's actually just one thing. In general, what this means is planning becomes a multi-objective optimization problem. Multi-objective optimization problem. And if you have a multi-objective optimization problem, how many of you have heard of multi-objective optimization? Yeah, okay. So you are the one who's going to do ORT, right? Yes, not surprising. So again, see, understand, it's a simple thing called planning that you signed up for, and it turns out if you really want to understand anything, you need to understand the entire thing that's connected to it. As you lift it, then a whole bunch of, science comes up. Okay, so multi-objective optimization is beautiful in the following sense that you normally think of a single objective, it essentially you can do this business of look for maximas and minimas in the loss function or the optimization objective function. But if the objective is not single dimensional, it's a multi-dimensional, right? Then essentially, okay, let me just take a picture of this. Okay. So imagine a simple scenario. You have, suppose you have plans where the only thing is cost. Then if I have plan P1 and assume in such a way that normally make it in such a way that the axis is such that as you go from right to left, it becomes better. So that basically, since cost is a bad thing, you will think in terms of 1 by cost. Right? Like, if you think of 1 by cost, and if you have P1 here, P2 here, which actually means P2 is cheaper than P1, that's it. Basically, P2 is better. It's a single dimension. Right? So now, in the case of multi-objective optimization here, you can have 1 over cost. Basically, as the cost reduces, you're better off. And similarly, 1 over time. The less time, the better, typically. I'll assume that's reasonable, although some people actually might just assume that the length of the airplane travel is what gives them true happiness. In which case, have you guys heard this joke that these Americans go to Britain and they're in this long queue for a museum or something, and then finally they are just about to reach, and there's this British couple in front of them, and those people are right in front of the window, and they say, let's go stand in the other line. The idea being that Britishers just like queues. They're optimizing a different metric. They're increasing the amount of time they stand in the queue. You guys, on the other hand, want to cut the queue. Most of the rest of the world cuts the queue, right? So anyway, so assume that 1 over time and 1 over cost, right? So the question, of course, is I have a point like this. This is P1. Okay, and then another point like this, P2. Which is better? What?
The time and cost are like normalized to how much they matter to you.
Yeah, the point is, by the way, if people say they have multiple objectives and everything can be converted into dollars, they have a single objective. The reason we convert everything into dollars, saying a human life is worth whatever the money we have to pay if we run over them, right? At that point, this is not multi-objective. It's just the amount of money that I'm saving, right? But notice that even in the imperfect world we live in, if you get jailed for 12 years, you don't get to say 12 years instead. Why don't you take 12 million? At least you don't get to say it. Some other people in the politics get to say it, but you don't get to say it. You probably are likely to have to actually sit in the jail for 12 years. It's kind of sad. So it's a different dimension altogether. So the whole point of multiple dimensions is they can't actually be combined. If you can combine them, it's a single dimension. And one way people handle multiple dimensions is just say alpha times apples plus 1 minus alpha times oranges is equal to happiness. Right? That's basically a single objective. At which point, who are you trying to impress, saying there are multiple objectives to be? People do it anyway because it's easy. That's the reason why we invented money. Because otherwise, the bartering system is too darn painful. Like, oranges they have this oranginess, apples have their appliness, and then cars have their cardiness. And so it's like everything is in a different dimension. So you owe your friend an apple, then you don't give them a car, they won't be happy because you owe me an apple, so you should give me an apple. No amount of cars can make up for an apple. Remember, the only time we say this is no amount of money can make up for the death of my loved one. That's the only time we actually mean multiple objectives. Whenever we are ready to take the money, that means it wasn't a separate objective. You're just sort of telling yourself it's a separate objective. Right? So if it is a different objective, then do you realize, so P1, P2, and then also P3. Is there anything you can say about P1 and P2? Is one better than the other? No. Because some people might like shorter flights, some people might like cheaper cost. So both are possible. Is there any bozo you know who might consider taking P3 versus P1? So this friend basically, so you're saying you have a one flight that's $300 and 3 hours. Another flight, it's $800 and 8 hours. That's what I'm saying. And so if you have any friends who say, yeah, give me the $800 8-hour flight, those are your English Q people. They want to increase the amount of time they spend on the flight. They have nothing else to do in life. Right? By default, essentially, people think shorter the time, the better off. You see what I'm saying? So essentially, I would argue that $800 8 hours flight would never be chosen by any rational person over $300 3 hour flight. While a $300 3 hour flight might be chosen over a $300 3 hour flight might be chosen over a $500 2.5 hour flight. There could be some people, okay. So this is why when you have multi-objective optimization, this is called Pareto curve. Pareto curve. And this guy is called Pareto dominated. And answering a multi-objective optimization problem is finding the Pareto curve. You are living it, but you did not know the name, essentially. You understand what I'm saying? This kid knows, obviously, because he spent that time. And he also will tell you that it's too hard. So after we understand this, we will then say alpha times time plus 1 minus alpha times cost. We'll call it a separate thing. We'll just do this. And as I always said, the difference between a computer scientist and a hacker is that computer scientist basically tries to do the right thing, realizes it's too costly, and gives up and does the easy. Okay, the hacker doesn't know and doesn't care. And so if you just ask LLM, then you're a hacker. Because you don't know and don't care whether it's optimal or not, whether it's the right thing or not. You understand what I'm saying? Okay, so that's basically what happens for true Pareto multi-object optimization. In the case of SAPA, what happens is you have time and cost. And if you read the rest of the paper, I asked you just to read the search queue, which I will talk a little bit in a minute. But what the reason actually that paper is interesting is because he winds up using planning graph heuristics. Planning graph heuristics to estimate cost to go and time to go of a partial plan. Even though he does the actual optimization in terms of alpha times cost plus 1 minus alpha times time, it turns out that since time and cost are two very different natural quantities, it's easier to estimate them separately and combine them. Do you understand what I'm saying? This is actually one of the things that, basically it turns out that time to go and cost to go can be separately evaluated. If you look at the rest of the paper, maybe there'll be slides there. You actually get to see how the cost varies as the time goes on. The cost estimate varies as the time goes on. Okay, so that's one of the important things about the multi-objective. And once you have the multiple objectives, if you're anyway combining into a single objectives, then you need quote-unquote hyperparameters. Right? You have alpha 1 times time plus 1 and alpha 2 times cost plus alpha 3 times gas plus alpha 4 times number of atoms. That would be my optimization. And interestingly, if you actually are trying to understand somebody's reward metric, which is basically inverse reinforcement learning, right, then you are essentially then trying to estimate the alpha 1, alpha 2, alpha 3 based on which plans they seem to like. Right? If you present these kinds of plans and then ask which one do you prefer, and they give you a preference relation, you can then basically convert that into a consistent hyperparameter combination, if it is possible, such that that will capture what it is that you're actually doing. All of these are different papers, different textbooks, different everything. But without understanding it, you just say, temporal plan, you just say, fine. You need to know at least the place where the rabbit hole starts, so that if you decide to go, you go. That's the whole point of grad courses. I need to show you all the rabbit holes so that you can get into it if you want. Right? Okay. Let's see a couple more things and then we'll take a break. Yeah, you know about concurrency. We already talked about it. And one of the only things I do is required concurrency. If a problem requires concurrency, that means every plan in it requires concurrency between some pair of actions. And if a domain has one problem that requires concurrency, then you say the domain requires concurrency. Okay, this is the usual way. Normally, you talk about NP-hardness too, in the sense that you say a particular problem class is NP-hard if in fact there exists at least one instance that cannot be solved in quantum. Right? So if you think in terms of temporal plans actions in strips actions, temporal planning actions in strips action point of view, then you want to think of strips actions. Remember, I was showing you the planning ordering relations, and wrote that A1 less than A2 can be written as A1, A2, 0, infinity. So whenever you get a more general representation, you want to see what the special case gets represented in this general representation. Otherwise, it's not a general representation. So if temporal planning is truly a general case of classical planning, then how do you represent strips actions in temporal planning? One idea would be to just say instantaneous. That means actions are instantaneous. They have no start and end point. They have one point. The problem with that is that's physically impossible. Nothing in the world is actually instantaneous. It's just an abstraction. The other is to say they have epsilon extent. That means each action has an epsilon extent, and then so that is P, S and PE, TS minus TE is epsilon. That will be a way of thinking about it. Yes, go ahead.
So how do you determine how many maximum parallel actions you can do at a time when you're going?
No, if they can allow it. Basically, the question about parallelism is only about interference. And the interference can occur either because of resources or because they're killing each other's conditions. Okay? So that's the epsilon duration one. And the other one, you can also have something which has a normal duration action, but its preconditions are overall preconditions, and the effects are always at end. In which case, it's just syntactic sugar. Even though the actions are kind of fat, they really are now different from Stick's actions. And part of what we talk about, if you read the required concurrency paper, the temporal gap doesn't exist there. Because you say that an action representation has temporal gap, it has no temporal gap if there exists a point, one point in that action at which all preconditions and all effects must be true. If on the other hand preconditions are ending here, effects are starting here, there is a temporal gap. And you didn't have to talk about temporal gap in strips planning because it is instantaneous action. If you have an at overall precondition over an alpha size, over a durative action, and then at end effects, then again there is no temporal gap because there exists the end point where all the preconditions as well as all the effects must be true. You see what I'm saying? Okay? That is the place where it turns out, if you have that representation, then you cannot essentially express problems basically that require concurrence. Those are temporally inexpressible. Okay? What else? That's the temporal gap that I was just talking to you about. And there's a huge number of brand names of planners, but I just want to talk to you a little bit about SAPA when you come back, because you already read about it. Then we'll discuss a little about the required concurrency paper, because you also read about it. Okay? And then I think I already kind of broached the subject of hierarchy, right? Because I did all this A1, A2 stuff. So it would be quite easy to transition into it when we come back, even if I don't get to start it here. So 350. Yeah.
In my class on reconfigurable computing that I'm taking, we just did a Pareto front on like the resources on an FPGA, like the DSPs and the LUTs, but those sort of feel like one-dimensional because when you're given an FPGA development board, you have a maximum of each.
No, the fact that there is maximum doesn't mean anything. The question is, are you combining them into a single apples plus oranges number? That's very important. And in general, to be completely honest, again, as I said, for something to be really a different kind of a problem from single dimensional optimization, if it's a multi-dimensional optimization problem in a true sense, it must be thinking in terms of Pareto sets, because that's the only solution concept for it. So you can't talk about give me the optimal plan, because there is no optimal plan when you have two dimensions. You have a Pareto set of optimal plans such that all of them are incomparable, they're as good as any. And anything below that set is essentially Pareto dominated.
Okay. So, with these Pareto curves, what if you have like two plans, right, and they have the same, like ratio of 1 over time to 1 over cost, but one's further, in the diagonal than the other.
Again, if you have any other thing, then basically you're putting extra constraints. Then basically you are saying something crazy about some scale invariance and R. For example, things like, one of the things that you might have in mind is the difference between 10 and 9 is bigger than the difference between 10,000 and 9,999. That basically means you have a certain scaling factor, which is very different thing. Yeah, exactly. Yeah, and in fact, one of the things that people talk about really ultimately is this notion of utility, and you talk about utility of money. And utility of money is like that, essentially. It's a kind of an S-curve. You know, people tend to give higher negative reward when they lose money. And if you got 1 million, getting another 500 from that 1 million doesn't give you as much happiness as if you have only $10 and you got $500. So that's why this curve sort of flattens out. You know, it's not all dollars are created equal.
Yeah.
That's basically, so utility is not equal to dollars. This is dollars, this is utility.
Okay.
And you know, you can explain people's behavior in terms of this. I mean, again, all of this stuff is discussed in, you know, in intro to AI classes, etc. Because this sort of explains, for example, why poor people buy lottery tickets, rich people don't. Why? Because for poor people, essentially, the expected reward in terms of if you hit big, then you'll make this thing is so much higher. Whereas the same $1 million for Bill Gates is nothing. So people who are rich enough don't ever buy lottery tickets. And so you can either say poor people are stupid, or you can say poor people are actually rational with respect to this reward system. In general, one of the things that utility theory says is that nobody is really stupid. You just need to understand what their reward system is. Those Britishers who decided let's shift the queue are not stupid. They just have a different reward system.
Okay.
And to understand people, you want to understand their reward system.
Yeah.
Essentially, because capabilities are approximately the same, you know, and not all of us are basketball players, but there's approximate set of capabilities. But our behavior is much more determined by our rewards, what makes us happy. And they can change pretty wildly from people to people. Okay?
That makes sense. Thank you.
Okay.
I have a quick question. So in the language where for an action, like where the effects are appearing before the preconditions, so I'm not able to wrap my head around that
What?
concept. So in HT
This thing?
so in this case,
Oh, just give me a
so in this case, like, you have an action here. You're seeing that like if the precondition it appears like maybe towards the end of the action, and then the effect appears in the beginning of the action. I'm not able to wrap my head around this concept as to like what would a real world equivalent for this be.
Well, I mean, again, the point is that particular one, right? I mean, sometimes actually you might very well have, you probably almost can grasp your head over for all P and E comes in the beginning itself.
Okay.
And again, these are not the most normal actions, but if you're thinking in terms of variations, you're talking about it from that hierarchy perspective.
Yeah.
Right? That hierarchy is a lot more theoretical hierarchy than, and so basically what we are saying is, once you start an action, it gets to say that I must have this precondition at the end for me to end it. Okay. So if you don't have it, that action's execution is not well defined. But as soon as the action starts, you already get the effect.
Got it, got it. Maybe I was thinking about it from taking an example like where you have.
I mean, the physical significance is harder to grasp because in general preconditions come before effects most of the time. Right? Yeah. But all this is saying is it could very well be that, again, I think maybe you would not have been surprised, for example, if some effects are occurring in the beginning, some are occurring in the end, and some preconditions are in the end.
Yeah.
But I would argue that essentially it's very similar. It's just that this precondition is required for correct execution of the action. That's
Makes
it.
sense. Makes sense. Got it, got it. Yeah.
That's all it means.
Yes. Got it. Thanks a lot.
Okay.
Appreciate it.
Yeah.
You mentioned inverse reinforcement learning, and is that connected to inverse objective?
No, in general, inverse reinforcement learning is given the behavior, figuring out what the reward metric is. You know the MDPs, right?
Yes.
So MDPs are determined by basically the transition metrics and the reward metric.
Fortunately, I learned.
What?
Fortunately, I learned that inverse RL concept this week other students presentations. So
Yeah, that's the same thing. But inverse RL is just nothing but learning the reward.
Yes.
And typically the reward, your behavior kind of gives me a sense of your reward. Right? So figuring out, given your behavior, I'm trying to compute what your reward must have been. Assume that you are an optimal agent, rational agent. Then your behavior must have been optimal with respect to this unknown reward function. Right? And I'm trying to figure out what that reward function is such that your behavior will be optimal. So you see multiple trajectories of behavior from you, and then it's essentially trying to, and they're all optimal with respect to some unknown reward function. And what you're trying to do is learn the reward function. That would make all of them more or less optimal. And it'll become sort of and there are ways of setting up the learning such that it's actually inverse reinforcement learning is not at all reinforcement learning. It is basically just simple, like learning, like a latent variable.
yes, and then after that, after we get the unknown mirror from inverse reinforcement learning, and then that mirror is treated as a single ultimate values each one.
No, this is basically, this has nothing to do, my point is, reward function by definition is single dimensional. Normal MDPs have reward in each of the states. That's a single dimensional optimization. There is no multidimensional at all. If you have multidimensional, then each will have two different rewards. Imagine there is both time and cost rewards. Then there will have to be like a tuple as a reward function. Nobody does that. Most people who are doing reinforcement learning now will just assume single objective reward. Single reward point per state, which means single objective optimization. Okay, but once you get the reward, then you can essentially, so you already know the transition matrix, and you are trying to basically imitate the person who is showing the reward, the behavior. There are two ways of imitating the person. One is look at their trajectories and try to imitate those trajectories next time. That's called imitation learning. The other is take the trajectories and decide what reward function should be such that these trajectories would be optimal with respect to that. And if you did that, then I can imitate you with basically much better because I actually know your reward. So you can go much more out of the distribution, right? Because the reward function is known now. So I can essentially just basically, I have an MDP with transition function reward metric that corresponds to you. So I can just know exactly what you will do any given point. That's the difference between imitation learning and IRL.
Oh, yeah. I think I missed your words. So what was your point to introduce inverse reinforcement learning?
No, inverse reinforcement learning is what is the reward. So in normal MDPs, you're given the transition function and the reward function, and you are trying to compute the optimal policy. And once you compute the optimal policy, the trajectories of that optimal policy are the behaviors that you will see the agent exhibiting. Now imagine you have another agent, you know its transition matrix, that is imagine because you know the transition dynamics, and you see its behavior. Assuming it's a rational agent, it must have been exhibiting that behavior to optimize its rewards. So then what is the reward? Imagine I didn't give you the reward. So I want to copy you. To copy you, I just need your transition function and reward function. I know your transition function. I don't know your reward function. Instead, I have your behaviors. So from the behaviors, I can either try to blindly imitate you, Or take the behaviors, reconstruct the reward function, put that into my MDP, then I don't need you. That is called inverse reinforcement learning. There is no reason why the name makes sense. It is reward learning. You should think of IRL as reward learning.
Yeah. I understand the concept of inverse reinforcement learning, and then what was your point to mention that at your previous?
When did I say what? When did I mention what? I don't remember.
You mentioned it when it comes to multi-objective function, and when it comes to...
No, but in general, the point is, if you know somebody's behavior, you can learn the reward, implicit reward from that. And so one particular idea would be, imagine that there are 2 dimensions, and you assume that their reward function is alpha 1 times time plus alpha 2 times cost. Then I just need to figure out alpha 1, alpha 2. That is what IRL does for you. That's reward learning. Because every learning, we have to do is afterwards, you can stop by class, but every learning algorithm, when I say reward function can be gazillion different functions. I need to put a bias. I need to say it's a linear function in terms of states or something. Here I'm saying it's a linear function in terms of the objectives.
Yeah.
Then I just need to figure out what the alpha 1 and alpha 2 are. That's all I meant.
Okay, thank you, Professor.
Okay. Acharya Varadapur. Tejas Anvekar. Rhythm Arya. Cho Wusong. What? Okay. Soham Chowdar. I think that's gone. Vivek Reddy, Sri Rakesh Gajar, Vardhan Gangal, Kumadi Venkata, Gabriel Habib, Rawan Halder, Jaj Baz, Joby Perangatu, Marco Jojic, Damon Jung, Shai Saket Kambalapalli, Ravi Kanmuri, Inshuan Lu, France Malapo, Kush Manchanda, Ram Menon, Luka Michovic, Sarthak Mishra, Nived Mudiyam, Sania Mulia, Jayesh Nagpal, Neem Nuan, Manav, Skand Pravatikar, Jaya Aditya Pavluri, Rishita Reddy, Prasad Tarunya, James Price, Ryan Pua, Muhammad Rahil, Arjun Ranjan, Mohak Rathod, Yash Sawant, William Sirovic, okay, Shaheen Taha, Ashish Shekhar, Lavinder Singh, Rodney Staggers, Jonathan Stedham, Ethan Tang, Manya Tiwari, Nitran, Brinda Uday Kumar, John Woods, Saida Zamod. Okay. So if you are here and you didn't get the attendance, make sure that you tell me before we leave. Okay. And also I should mention for just completeness sake, okay, let me see. I will start the recording. What Groucho Marx said, that the man who won't read has no advantage over a man who can't. Man who doesn't listen has no advantage over a man who doesn't show up. Of course, you get attendance. And by the way, if you stand here, you will know exactly who is paying attention. You know, you always think that somehow teachers have 15 eyes. No. You stand here, you will know who is paying attention, who is not paying attention. It's extremely hard to kind of pay attention when you are looking at your, whatever you're doing with no actual reaction to anything. I don't think I'm Seinfeld level, funny, but I'm sure I'm saying things that are sometimes funny, sometimes surprising, and you look the exact same stunned person doing their work, then you are that Groucho Marx person who won't read. And so you deserve, basically, you get attendance, but you're basically wasting your time. Okay, that's that. Yes?
So I just wanted to ask what Pareto optimal is. Is it on the curve?
No, Pareto optimality, so basically anything, these are called the Pareto curve, and everything that is on the Pareto curve are called Pareto optimal solutions. So in general, the question, one of the issues is there is this notion called solution concept. And for different problems, there are different solution concepts. And if you have multi-objective optimization, then you are not saying what's the optimal plan for this multi-objective optimization problem. There is no such thing. The only thing that is well defined for a multi-objective optimization problem is the Pareto curve. Do you see what I'm saying? So that's the thing. Similarly, if you have multi-agent situations, then the only things that are well defined are equilibrium. Things like Nash equilibrium. So those are called solution concepts, and you need to understand what is a reasonable solution you can hope for that problem, and then compute that. As against, I have multi-objective optimization problem, give me the most optimal solution. There is no such thing as most optimal there. You see what I'm saying? You should at least understand there is a Pareto curve, and then I want to combine apples and oranges into some hook, and then call that my objective, that will be fine. Right? So you need to understand what is the solution concept for any problem. So for example, similarly, when you get to something like MDPs, for something like MDPs, what is the solution concept? A policy is the solution concept. A policy is basically what is the action to do in each state. And actually, a mixed policy is also a solution concept. A mixed policy tells you what is the distribution over actions that you get to do in each state. That means this is the most likely action, this is the next likely action, etc. Right? And if you have S number of states in the MDP, and there are a number of actions, then the total number of policies is a power S. Maximum number of policies can be a power S. Maximum number of mixed policies can be Maximum number of policies is a power s. Mixed policy basically tells you for each state, here's the distribution. 2 power what? Okay. Any other answers? What?
Is it infinity?
Yes. I mean, if I'm not happy with any finite, just go with infinity. And if it's a really advanced class, we'll talk about all of infinities, different levels of infinities.
Or it's like you have a real number.
Because the point is that distributions, if you, for each state, right, essentially it's a power s, because in each state, you can do one of a different actions. And there are s states, a times a times a times a times a, s times, so a power s. So if you have mixed policy, then what happens? In each state, you have a distribution over actions. Even if you only have 2 actions, there are infinite number of distributions over 2 actions. Just get 2 real numbers that add up to 1, and they are greater than 0. They are called simplexes in general. So the number of mixed policies is infinite. And one of the things that you may or may not be noticing, and by the way, I'm making enough digressions, so might as well do this too, is that for MDPs, for those of you who know MDPs, if you don't know MDPs, again, what can I do? You're in like an advanced AI class and you don't know what MDP is, what can I do? So in an MDP, essentially, you only look for the what's called that deterministic policy. The policies are deterministic. For each action, each state, there is only a single action. Even though there are infinite number of mixed policies. And it turns out there is a beautiful theorem that says for single agent MDPs, if there is an optimal mixed policy, there is also an optimal deterministic policy. And they are equally optimal, in the sense they will get the same expected reward. Do you understand? Which is why you can do deterministic policies, look for deterministic policies. There are 2 places where you would stop doing deterministic policies. One is in games. If you have another, so basically, did I tell you the rock, paper, scissors, Lisa, Bart example? So Lisa and Bart basically are trying to decide something, and they can't decide which, whether to go to the movie or go to the like bowling alley or something, and they can't decide, so they will try to do some rock, paper, scissors. And so they say, let's play that rock, paper, scissors. And then there are 2, bubbles on top of their heads. Bart is saying, yay, we get to play rock, paper, scissors to decide something. And Lisa is saying, yay, we get to play rock, paper, scissors. And Bart always picks rock. And if you don't understand this joke, you never played rock, paper, scissors. You see what I'm saying? I mean, you don't need to go to the rock, paper, scissors, spark, all that stuff. It's just rock, paper, scissors itself. There is, if you have a deterministic policy, you are screwed. You always pick rock, then, basically paper covers rock. So I'll always pick paper and you're dead. The whole point is keeping that uncertainty. So for the games, you must search in the space of mixed policies, multi-agent things. The other place where it happens, crazily enough, is even if you are actually trying to solve single agent MDP policy, if you want to do policy gradient method, policies are discrete. Gradients are not defined for discrete quantities. So convert them into continuous quantities, even if it increases the number of policies you are looking at. So what you will wind up doing in policy gradient is you think in the space of mixed policies, which are essentially distribution at each state, the distribution over the actions. And if you have distribution over the actions, you can do epsilon change to the distribution, You can't do epsilon change to, it's either A1 or A2. Can you change an epsilon change such that it's between A1 and A2? There is no such thing, either it's A1 or A2. But on the other hand, if it's A1, A2 with the distribution 0.4 and 0.6, then I can do 0.39999 and 0.600001. That's epsilon change. You guys see this? Crazy nonsense. But this is how math helps, because you need the gradient, so you will convert the discrete stuff into continuous stuff just so that you can get by. Okay. Anyway, so this we got into this because solution concepts. Solution concepts have to be understood. Are you talking about deterministic policies? Are you talking about mixed policies? And if it is, and sometimes you might wind up looking for bigger than what is needed because it's actually easier to learn, to optimize for that, or learn that in the case of policy gradient. Very, very strange stuff that happens. You're looking actually for only what's the best out of A power S policies. And you decide, I'll search in the space of infinite number of policies. You would never have thought it's a not reasonable thing to do in grade school. But that's how math works. Because basically, at least you can follow the local gradients. Okay. Okay. So brand names. Okay, so 450, right? Yeah, so there are multiple approaches, of course. So this is basically the SAPA representation. I'm just kind of going over it, but you read them already, I think. So if you have any questions, stop me. So you are basically durative actions. The start plus duration is equal to the end, and instantaneous effects can be there. You can have preconditions at a point or over a period, which is basically overall preconditions. And so here is, for example, flying action. It basically requires preconditions and is giving effects on the top. And the effects can be, so one of the funny things is, it's a reasonable thing that when you're flying, as soon as the plane takes off, you are symbolically no longer in that city. I don't know if you guys actually ever flown international flights that make a stop in the same country. I have done this once. I was flying from Calcutta to US, and the plane actually stopped in Delhi too, just to get a few more people. But they made it very clear too that we are no longer in India. The people in the plane are no longer in India. The people outside are in India. They can still come into the plane. They will no longer be in India. Our Indianness is gone as soon as we left Calcutta. That's how international things are defined. You see what I'm saying? Okay, so it makes sense that as soon as you started flying, you're no longer in that city, symbolically speaking. And then when you reach the other place, then you are in that city. So that's how you're basically modeling this stuff. And then there's, of course, the fuel is being consumed over the entire time of the flying, and you need a precondition saying at no point is fuel should be less than 0 or equal to 0. Okay, that's like our safety constraint. And so basically, you can have conflicts between the actions either because of effect conditions, that means one guy is violating the other guy's precondition or something, or just the resource contention. Do you see what I'm saying? So basically, I am consuming this fuel, you are also consuming fuel, or I'm consuming fuel and you are producing fuel, so we are interfering, essentially. And then this basically was the thing about the required concurrency. Actually, let me get over this. I'll come back to this in a minute. Okay, so this basically was your SAPA description, right? So it thinks of plans as this set of constraints. Okay, P is the condition and where the time at which that condition must be true. And then M is the set of functions that represent the resource values. So that function basically tells you how the resource will change over time. Pi is the protected persistent conditions. That means over this interval, this condition must be not touched, must not be touched. Okay, and then Q is the event queue. It contains actually essentially, remember there's a clock time right now, that is T, okay? But there are, because you started this action, you know that certain things will happen later in the scene. The moment you committed to the action, you committed to all its effects. You don't get to say abort, abort. Of course, unless you have an abort action, which can stop an action in this thing. The moment you start the action, it's going to end. Right? So basically, there is a bunch of things that you know about the future. Weirdly enough, right? You knew before everything that was there in the beginning, but now you also know things that will, you know for sure will happen in the future. These are because of the commitments you made to put certain actions, and those have delayed effects, and those effects will occur exactly at the time they're supposed to occur. So these are requirements, and these are events. These are things that will happen. And if you understood SAP algorithm, basically what it does is it does this fattening and the time advancement. In the case of fattening, essentially it is just adding more actions that will add to both the event queue and to P and pi and everything except keep the T same. The time clock hasn't changed. And if you decide to do the clock advancement, then you change the T. Normally, T can be changed to any other number compared with that's higher than the current number. That's it, right? But that means there are infinite number of places to change the time to. And one very reasonable thing that would look like a reasonable thing is look at the event queue and see when is something interesting going to happen next, and shift yourself up to that point. Remember, time is always, because this is SAPA, right? So this is actually temporal. You know the start time, so you know when the effects are going to happen. This is state space. It's not, time is not lifted variable. You have actual numbers for this. So the event queue will say P will occur at 17, time 17, Q will occur at time 16, M will occur at time 17, 75, etc. So that means Q, which occurs at 16, is the earliest event. So if you're going to shift the clock, you're going to shift it to the earliest event in the event queue. And when you do that, the event actually occurs. Then so you remove it from the event queue. That is basically progression. So you know the state has changed. You see what I'm saying? So the point about SAPA is it looks, if you look at it like this, it looks very complicated. But what I was telling you last time is you could have done progression essentially in terms of fattening and lengthening. And if you understand that concept, shifting from there to here is like epsilon difference. You see what I'm saying? And again, in the fattening and lengthening, for the classical planning, we didn't have to deal with when we shift the clock, how far do we shift the clock? Basically, it's like to the next instant. The next instant is basically the next instant. It doesn't matter what it is. But if you have metric time, then you get to decide, would you shift it by 3 seconds, 15 seconds, 5 days, 17 days? And that's where SAPA had to figure out how to make a discrete number of epochs. And a reasonable idea was, we'll shift it until the next interesting thing happens. That looks like a very reasonable thing to do. Unfortunately, it turns out that if you have a temporally expressive problem, this kills your ability to be complete. And again, one of the other things that you have to think about in terms of completeness is completeness is an inductive property. You see what I'm saying? You need to prove that your solution, all of these are properties, right? So completeness is an inductive property. You need to be able to prove that for every problem which has a solution, you will find the solution. Because empirically, you might find you might run out of time. The fact that you run out of time cannot be said to be showing that the search is incomplete. It only means that, that what I'm saying is if you give infinite time, will you ever have found the solution? If there is a solution. That's completeness. Do you understand what I'm saying? People tend to confuse it as, oh, I tried, I ran it for, I asked LLM for 80 times and it failed, and so basically there is no solution. And the question is, if I ask infinite number of times, would it have found the solution? That's the real question of completeness. And what we are saying here is, even if you basically let it run forever, it doesn't exist in the search space. So there are two ways in which search algorithms can be incomplete. One is the thing that you're looking for doesn't even exist in the search space. In which case, it doesn't matter how you went through the search space. The other is, it is in the search space, but the way you are going through the search space is inadmissible, like depth first search, for example. Because of which, even though it is there, you went off in the deep end into this rabbit hole instead of looking at this solution that is in the 50th layer. Those are two very different concepts. And in practice, you can't tell the difference because you just say that it didn't get a solution, so that's it. But we are actually talking about those kinds of distinctions. Okay. So anyway, that was the point about the required. That was the point about how SAPA works. This is the timestamp, of course. The search algorithm pick a state S from the queue. If S satisfies the goals, remember this is the state S. This is the state S. In the classical planning, state S was just a bunch of fluids. But here the state is these predicates that need to be made to be true somewhere else, these resource functions, these protected conditions, these events, and this thing. Okay, yes?
So using the plane example, like what if you had a goal that's like crash in the middle of the ocean, right? And so could you, with this search space, generate events where like you start the plane without enough gas?
No, remember that, please understand that there is essentially the events here are completely determined by the actions you chose. There is not much of a mystery here. Each action is a durative action. So you get to pick an action to support a condition. You pick an action and put it. The moment you put an action, then the conditions will be added to P, and its resource condition will be added to M. If it has any persistence condition, it will be added to pi. If it has any delayed effects, they will be added to Q.
So you could not have actions cut short in this model?
In this, no.
Okay.
Yeah. In this, no. Again, interesting that you could ask this question, right? Because real world planning that we do is a lot more complicated than even this. And this is already a lot more complicated than classical planning. And the interesting part is, on one hand, we are alive, which means somehow we blundered through without dying. And it's mostly because we stabilized the heck out of the environment. Survivor bias. There's a whole bunch of bozos just like us who died. Right? And sorry for them. But we are here. Okay? On the other hand, so basically we stabilized and we are able to live. Somehow we made. So we are doing very costly planning, but there are no guarantees. We just are doing something. And if it works, we take credit. Like especially the best things are economic planning. Right? I mean, the Fed decides what's the right thing to do. And there are beautiful analogies about it. Like, for example, trying to deal with the economy of a large country by just setting interest rates is like trying to fly a fighter jet with just a brick that you get to lift at the top. That's the only thing you have. And if it works, you become famous. And if it, if it fails, you become infamous. But you still have to get through the current precedent. Even if it is going to, the point is, even if it is working, it will only be found to be working 10 years from now. And the election cycle is 5 years, and 4 years. And the current president would like it to be that, let people be happy right now. I don't care about what happens when under the other guy's thing. Cut the interest rates. And so if I can somehow stop the economy from going to minus infinity until like 20th of January of the next election cycle, I'm fine. It will be the other guy's problem. You see what I'm saying? So when we say we're doing the planning, it's because we actually have no guarantees of any kind. Okay, so but the reality is, yes, there are more complex planning problems, but even giving any guarantees for even simple planning problems is pretty hard. And that's what I'm hoping we will get. Okay, so yeah, pick a search state from the queue. If S satisfies the goals, then end. If not, non-deterministically do one of them, advance the clock, which is by executing the earliest event in the queue. Executing basically means now the time has gone further, so then now actually the state actually has this thing true right now already. And then apply one of, other possibilities, apply one of the applicable actions. And to check whether the action is applicable, you have to make sure that its preconditions are consistent and effects are consistent with the pi, especially pi basically, because if you are trying to keep something constant and if this action is going to kill that, you can't put that action. Remember, pi basically may be saying you need to keep this condition true from time point 5 to time point 75, while the current time is only time point 20. Because you made a commitment that up until then you will have to keep this around. And so if you're putting in an action that actually kills that, then you're in trouble. So that's the interesting kind of interference. You can't put in actions that are actually going to kill the required commitments. Because some actions can be very long. And they may be like a for all over them. And you're putting a little action in the side which actually kills that for all. And that's interfering. You see what I'm saying? That's what that paper is basically, that little algorithm that you read, basically that's what you need to understand. That's what it's saying. Okay. So anyway, so what is the goal satisfaction and what is the action application? That's the definitions. So for the goal satisfaction, you will say that a state implies goal for every condition pi, ti belonging to the goal. That means a goal is always just a bunch of things that need to be true by certain time points. In the classical planning, it's like a bunch of things that need to be true by the end of plan. Here it could be, this must be true by t equal to 20, this must be true by t equal to 75, etc., etc. So for each of these goals, so goals themselves will be like this. So you check if that goal already corresponds to p, okay, and such that the times that it's already been achieved. That means you are actually, the goal that needed to be true has become true by the time it is required to be true. Okay? And also there exists an E belonging to the event that actually adds the goal. So basically the idea is you can stop, if you know that you started this action, and once you start this action, you take 200 units of time before it gives E1, and E1 is your only goal by 300 units of time, then I would say your plan is done. Because you know for sure that this action has been started, that means that other thing is going to happen. It's a guaranteed deterministic event. Because the action has been started. You can't get to stop. It's a single agent domain, so you can't stop actions. Nobody is stopping the actions. So that's what that thing says. My point is that these definitions look a little more complicated, but that makes sense. And you should be able to drill, given how the normal fattening works, you should be able to drill those. If not, I would ask you, what do you think you say when you say, I understood a paper? Honestly. Right? I mean, I'm pretty sure I can, you can present this without looking at people's faces. By the way, one of the great ways of presenting is never look at people's faces. People don't want to look at you, you don't look at them, presentations are amazingly good. Right? My sad part is I want to look at your faces. And if you are bored to death, then I know I failed. And if you're bored to death by choice, then what can I do? Anyway, so, and similarly action application, basically again the common sense points that how do you actually make sure that the action can be added. And when you add the action, then you need to actually update the data structures too. And this is basically what you wound up reading. Yeah, when is applied, then P is updated, and A is updated, the pi is updated, and then the delayed events Q also is updated. And there is an example that actually shows this in the paper. So that basically you know that. Okay. So again, the interesting thing is that, I mean, I made a big deal about the fact that essentially this idea solves lots of problems except the problems where they actually require concurrency. That was that paper that you read. And you might just say, well, of the big bad world, why do I care about the ones that require concurrency? That's a reasonable thing to do. Except the point then is, who are you trying to impress by talking about temporal planning? Because if, because if you, yeah, because I don't know if you understood this thing, essentially this particular slide basically saying, these are actions, but there are stars. The stars are the unique points where temporal gap gets eliminated. That means those are the points where all the preconditions and effects must be true at the same time. If there exists any single point in that action, then from the perspective of the algorithm, the rest of the action is just lying about. It's the point that matters. Do you see what I'm saying? And in which case, you look at it and say, oh, this looks like a concurrent plan. What do you mean that you can't deal with concurrency? But all I'm saying is you could have gotten this plan by essentially having this plan. And if you had that plan, this is a plan that where each of the stars is strictly preceding the previous one. Right? Which means classical planner could have solved this problem. And if you just wanted to impress your mom saying, look mom, I'm actually solving temporal planning problems, you call the classical planner, solve this problem, and then do a post-processing step. Right? So after, if this was the plan, so classical planner will find the plan, and then you do a post-processing step which compacts it, so that basically the concurrency is increased. Here the concurrency is an efficiency aspect. This is what I was talking about, multi-agents. If in fact it's a problem that can be solved by a single agent and you are adding more people, then it was not a multi-agent problem originally. It is just a single agent problem that you are improving the efficiency by adding more people. If on the other hand it's a problem that could never have been solved by a single agent, then it is a true multi-agent problem. So in fact there is a paper that I won't probably talk about here that again we wrote called what required simultaneity. I forget actually a different name. What was the name? None of you guys remember. So basically just like required concurrency, required cooperation. Required cooperation. Do agents have to cooperate to solve this problem? Or are they just cooperating to improve efficiency? You understand what I'm saying? A large amount of multi-agent stuff, single agent could have done it. It's the multiple agents will just try to improve the speed. In which case, you could have figured out how to do it with a single agent and then parallelize the heck up. Whereas if it cannot actually be solved by a single agent, then the space is a different space you have to search in. If you only search in the space of single agent plans, this picture is very important because without those, if there were no stars, let's say, then basically the point of this picture was that, even though this is a concurrent plan, this problem could have also been solved by a sequential plan. And in the classical planner search space, the sequential plan exists. You find it, you compress it, you will get your solution. If on the other hand, imagine there is no such plan. It is a required concurrency. That means every solution requires concurrency. Sequential planners will never find, they won't even have that in their search space. If you don't have in their search space, it doesn't matter how efficiently you are searching the space. That's the point of completeness. It's the same thing for multi-agent, required cooperation. And in fact, multi-agent RL is like a big deal right now. Most of the multi-agent RL is not multi-agent RL because it's just efficiency. It's not, it doesn't require cooperation. There is actually, as we speak, Upasana, one of the people who's helping with the class. By the way, I should mention that you may have noticed that Lucas had some personal issues and he had to take off time. And so he's not actually going to be the TA. I will actually change that. But the rest of the students are helping. As you see, if you did go to a, that's my RS file. The price of being an RA for me is that the class should not find. So they are actually helping. So if you are not finding somebody, it's not because, it's probably because you're not going. Office hours are not asking for questions. So there are 4 very good people, because one of them unfortunately is taking the course. And believe me, he has been put in a Faraday's cage. He doesn't know anything about what's happening in the course other than you. So the point is, anyway, Upasana essentially actually is doing work on this issue of multi-agent required cooperation, sorts of scenarios. And one of the interesting things is you can do cooperation by not actually cooperating. So I just stand, there are more people, and I just stand and I'll do my own thing, you do your own thing. And that can also sometimes improve the performance. Like imagine if there are like 18 apples to be removed from the table and put into a box. Right? One person has to take one apple at a time, put it in the box. 2 people, one person can start from that side, another person can start from that side and just put it in the box. And they don't have to talk to each other, they don't have to even interact with each other. They can glare at each other and then basically still be saying we're a team. So a team of rivals, a team of indifferent people. Required cooperation, on the other hand, essentially is there are like 18 these kinds of tables, and no single agent can lift the table. 2 agents are required to lift the table. They have to work together. And one of the things is there are benchmarks. One of the things that you have to understand actually, probably becomes clear to you because of the LLMs as well as the temporal planning as well as the required cooperation and as well as this other thing I'm about to tell you. I want to know when techniques fail. Because I have no startup, right? So if I have a startup, I just want to say that techniques work, just buy my technique. But I'm in the university, so I want to figure out what are the times they fail. That's a reasonable thing to do, right? And so one thing is any benchmark-driven research can be in the wrong direction because the people who made the benchmark don't know the difficulty of the problem to begin with. It's not like planning people are very smart, and they came up with a planning competition that just happened to have only domains that didn't require concurrency. It was a perfect combination. LLM people are not probably that smart, but they too came up with benchmarks that happened not to have any interactions and said planning is working. From the multi-agent RL perspective, there is actually a domain called overcooked. Today, for some reason, overcooked is making waves on the Twitter account. There is a game called Overcooked 2 or something. Anyway, so overcooked is essentially this kind of multiple people are cooking some various recipes together. Most of the setups in overcooked, which are supposed to be for multi-agents, don't require agents to cooperate at all. Right? And so one of the interesting questions is, if in fact they require cooperation, will they do well? And in the most recent paper that actually Upasana submitted, but also has a version of it in AMAS that's available on our webpage, she basically shows that multi-agent reinforcement learning policies actually don't require cooperation at all. If you think in terms of are the agents interacting at all, they don't have to interact at all. And so if you want interactions, if you don't have interactions, what happens is basically the agents are not actually. One of the great things that can happen with the human robots is robot says, yeah, that's good, and the human does anything. That can be possible. And you can say there are 2. In fact, first of all your projects are like that. Whenever there's a team project, there are 5 or 6 cheerleaders. And then one person who tries to do the project. Which is why I'm not a huge big believer in teams, because for the teams to work, they should actually be interesting teams where there's required cooperation. Mostly you have a team of 15 people, 14 cheerleaders, and 1 person who's, and sometimes apparently I've been even told by master's students that there are social conventions that if you are in a team with second year master's students and first year master's students, you allow the second year master's students to prepare for the interviews. I'm sorry, I'm giving away all the secrets for the master's students. And the first year master's students who are still not ready for the interviews actually do the project. I found out this because once long back I had a student who then came and said, I'm very busy with the project because my teammates, the seniors can't work and I have to make the project happen. So that's a team of required non-cooperation, where 15 of them don't do anything, 14 don't do anything, one does. But in general, understanding whether the benchmark actually requires cooperation and whether your algorithm is providing that required cooperation is very similar to what was happening in the SAPA thing. Yes, first and then yes.
So, Professor, you mentioned that single agents fail where cooperation is necessary. You gave that example of like if you require two agents to like pick up the desk or something. But I feel like that's, I don't know, I'm still not understanding this idea of cooperation being necessary because technically you could have like one super jacked guy at the table.
Yeah.
And like he would just be like big. So it'd be
No,
like,
that is completely fine, which is part of the reason why I actually said last class, I don't understand the whole multi-agent LLM literature right now, because LLMs are supposed to be super jack guards.
Yeah.
Why do they need multiple guards? Do you see what I'm saying? So,
Yeah, like
first of all,
yeah.
given any specific, first of all, you can't, here is an interesting thing, right? Given a problem specification, you have to ask, is the concurrency required? Is the cooperation required? If you change the problem specification, that's a very different thing. This whole issue is, if you guys are here, I would like one of you to kind of lift this and see. Saying that there may be a super jack guy doesn't help. There isn't one here, unfortunately. I know some of you are better built than me, but I don't see any of you being able to lift this, unless I'm just totally messed up and thinking that it's too right? So these are the agents I have. So you can't do planning with agents that you don't have, planning with actions that you don't have. You can say it's a great, easy planning problem, it's just you need to get the right action. That is actually generating the actions, by the way. So generate a new tool that will actually change the planning problem. But that's a different point. At any given point of time, you have constraints.
I see, that makes sense.
That's the point. I mean, it's a good point, but I mean, you have to understand that given, and the reason that's why I was saying SLMs makes no sense to me, because the whole point of LLMs is that they are super jacked know-it-alls. Then why do you need multiple know-it-alls?
I guess
Unless the know-it-all was not know-it-all to begin with. Right? Yeah, go ahead.
So you're talking about Overcooked too, and how Overcooked and how you can't really force cooperation. But like a game like Portal 2, where like each agent, in some cases it'll be like restricted to actions that one agent's able to do, but one's able to open pathways for another to get to another place. That's true cooperation? Or?
Yeah. So that's my whole point. That you have to come up with, again, all I am saying is there do exist domains that require concurrency. And if you are saying you are testing for temporal planners and you only have domains that don't require concurrency, then you are not really testing temporal planners. You could actually win the competition with classical planners followed by post-processing. And similarly for your thing too, that there are domains that actually require cooperation, and not all domains require cooperation. Sometimes the cooperation is done just not because it is needed, but because you feel like it. You see what I'm saying? Right? I mean, in fact, this you understand, this requires cooperation. But if you have too many teammates in your project, and by the way this happens, let me say this first, and you are supposed to lift the pen. Teammates know that if they are not playing a role in lifting the pen, they would not get any points. So everybody will put their small finger on the pen and lift it. That's forced cooperation, forcing themselves. This happens, by the way, when in the team projects, sometimes it becomes painfully obvious that one person actually did the project. The rest of them still want to say something in the presentation, because otherwise the professor will know too obviously that they didn't do anything. So they would say things like, and the introduction, and the conclusion, and the other person does everything else. It's true is cooperation, but it's not really required cooperation. the pen could have been lifted with one guy. The other guys are just there to get the points. Team projects are a great way to remember multi-agent work. You see what I'm saying? And you do this. I mean, we are smart. We know how to game the system. Again, I always said, I think the very first day I said, I want people who know that they can cheat and choose not to. Not even realizing that you can cheat basically means you are brain dead. That's no point. Right? You know that there are ways in which you can work the system, but you choose not to because, wow, seems like a nice guy, let's not do it in this class. I don't care whether you do it in other classes. Okay, but any other question? You had a question, yes?
Yeah, so I think there's like some connection, although not like super meaningful, between required concurrency and required cooperation.
Yes.
But it's neat that there are tricks to determine whether you have required concurrency, right? So I was wondering, is there actually like a interesting way to determine whether there's required?
So that's my papers page. If some of you have never gone there, I don't know what the heck they're doing. And there is Yu Chang somewhere. Actually, I could just say required cooperation. Yeah. That basically has everything I know about required cooperation. And it's kind of not surprisingly, it was done after the required concurrency paper. I mean, it seems to me that there's too much stereotyping going on in my life, but I guess I'm good at one thing, which is finding counterexamples. And I seem to be doing a lot. And it's becoming kind of painfully obvious, but that's you will learn something. Okay, so that's about the required cooperation stuff. You won't have to read it. If you want, you can read it. I won't make you read it right now. Okay. Yeah. Okay. We need to speed up. Yeah. So that's the temporal planning. The partial order planning can always be done. And we saw this thing. And then basically, the whole point of that required cooperation paper, I guess it will make sense to you right now, basically, is they were just showing that there are problems for which there is not a single sequential solution at all. And so something that looks for a sequential solution and tries to fatten it afterwards would fail, because it says there is no solution. That's how the completeness is lost, essentially. Okay. And then, of course, plan space planners don't have this problem. And in fact, I was just reading the paper, and first of all, I actually, I think there are certain parts that I believe even now I like the way they were written, maybe partly because I wrote some of them, but essentially the idea that what you're trying to avoid by doing the decision epoch planning is to not consider every possible time epsilon. And yet it turns out if in this progression version you can't do it. In plan space version, you can do it, but that's because you don't actually think in terms of times. You think in terms of time points, which are constrained. Simple temporal network already has infinite values for each of the time. And we no longer care about figuring out all the infinite things. It's just you need to find a correct dispatch that is consistent with the constraints. One of the weird things historically is nobody actually ever thought that progression planning can actually be done for temporal planning kind of scenarios. They assumed the only thing that will work is partial order planning. That's why I said Zeno was the first thing that was tried. But then it seemed to work, but then it was error. And the whole reason I'm saying this is to understand what is the limitations of an algorithm in general. Anyway, so yeah, that was the whole light match thing. You guys get that. Yeah, so this one is actually showing how the various data structures change, etc. I'll just stop here, but one of the other interesting things is that the rest of the paper, as I said, was plan graph heuristics for cost and time. That's really most of the rest of the paper. I didn't talk about it because essentially part of what I'm doing is you should at least need to know whether the plan is correct. If you do, because you're currently in this generate test mode, you'll have LLMs generate plans, and you test with your verifier. So I want you to understand first what the verifier is. Do you see what I'm saying? But the search part, but the required concurrency part was actually connected to the fact that if you're searching in a particular kinds of spaces where the solution doesn't even exist, then you're screwed. And which is basically what you were saying. Okay, so what else do I want to say? Yeah, so essentially the point about the temporally simple planning is that you can just do classical planning followed by scheduling. The scheduling essentially is changing the time points. And in fact, since I'm into that, let me show you that this can be an actual well described I just want to show you a paper that basically does position constraint, right? Yeah. That's a paper. That is if you are lemons, make lemonade. Right? If you have essentially generated, I said simple temporal problems are classical planning followed by scheduling. What exactly do I mean by that? So I kind of showed that animation, right? I said these are the things that were like sequential, but then I shift them such that they become more parallel, but it still be correct, right? So the interesting question is, in classical planning, if I give you a sequence of actions, can you find, if I give a sequence, that means everything is constrained to be before each other, right? Essentially, so if I basically said, if I basically said, A1, A2, A3 is the plan. Initial state is I1, I2, I3. Goal state is G1, G2, G3. This is my plan. Right now, this plan basically has the following structure. This is S0. And S0 is before S1, A1, which is before S2, A2, which is before S3, A3. Right? The question is, are all those orderings required? It works, but are all the orderings required? If I were to tell you the following thing, which is, here are my actions. A1 just gives G1. A2 just gives G2. A3 just gives G2. They have no preconditions. You already can see that those orderings are not needed, right? Right? But how do you do this generally? The way to do this generally is there's a very beautiful idea. Everything is a beautiful idea, but explanation-based generalization. Take this plan, explain its correctness using causal link proof, and check which parts of the plan took part in the proof. The other parts are not needed. Do you understand what I just said? Right? This is the reason you want to figure out how to different ways of actually proving the correctness. So if you actually prove the correctness by causal link proof, right? So A1 is supporting G1, A2 is supporting G2, A3 is supporting G2. Given this structure, all we know is the required orderings are A1 is before S infinity, A2 is before S infinity, A3 is before S infinity. Those are the only orderings that are needed. The rest are hanging around, doing nothing. So you just proved the correctness of a plan, and things of that plan that is not taking part in the proof are not needed to begin with. You understand what I'm saying? This is a very, very powerful idea. It comes up all sorts of places. If you can explain the correctness of something. By the way, how do you think most of the dependency analysis is done this way? Like yesterday, like this morning, I actually just uploaded a new version of the position paper on don't anthropomorphize intermediate tokens onto the archive. When you do this with the archive, essentially it basically makes sure that it basically says, hey, put the entire entire directory. So I do the zip entire directory. The zip contains all sorts of random stuff which is not needed. Then it asks, what is your top level file that you want me to compile? I pick the top level file. Then it right away says these other guys are not even relevant for me. I'll remove them. How did you figure this out? Because there are dependencies. The fact that they're all in the, it is true that if you have everything in the directory, it would compile. But you don't need everything in the directory for it to compile. You only need the ones that are required by the dependencies. That's exactly what we are doing. You see what I'm saying? If you do this in general, then you can take any totally ordered plan and convert it into the partially ordered version that is still correct without having to redo the plan. Now the question is, if you can do this is easy enough for you to understand, but what if I told you these actions are actually SAPA style actions? There are durations, there are concurrency, etc. And they are all position constrained. This action starts at this point, ends at this point, etc., etc. How do I fatten them without killing the correctness? That's what that thing is. Okay? In general, the powerful idea that you want to write down is if you ever tell yourself why something is correct, and if there are parts of the thing that didn't take part in that proof of correctness, they were not needed. If you remove it, you generalize. Do you understand what I'm saying? That's explanation-based generalization. And one of the interesting things is, here I have a clean theory. I have a clean theory of why, when a plan is correct. This is like a full clean theory. But sometimes I only have partial theories, and I generalize with respect to that too. Here is a classic example. You got down in Sao Paulo airport. Because at the end of the day, why not get down in Sao Paulo airport? You find the first guy who you see. A guy is wearing a pointy red hat, wearing a blue shirt, and speaking Portuguese. You are obviously you're an American, you want to generalize about everything, and so you said, all Brazilians are. What do you want to say? All Brazilians wear blue pants. All Brazilians wear pointy hats. All Brazilians speak Portuguese. Which one are you more likely to make the generalization? If you don't know, then you're in big trouble. Because you have an approximate theory. That nationality approximately, not in India, for example, this doesn't work at all in India. You get down in India, people talk Telugu, then you assume all people are good and they speak Telugu. But a huge number of people don't know how to speak Telugu. Sad situation. But in Brazil, it's well defined. Basically, nationality approximately determines the language. Nationality doesn't at all determine the color of the clothes. Those are called partial theories. And if you have these determinations, you can still use them to decide which features are relevant. And I know that all of you are into supervised learning. And one of the problems in supervised learning is a huge number of features. Most of the features, basically, if you give a lot of features, eventually the algorithm will overfit to those features. If you have a partial theory of relevance as to what features may be, how features may be connected to the actual class label, and you remove the irrelevant features, that's called the feature selection problem. Feature selection problem is basically what is explanation-based learning. The whole idea is you take one class and you get like epsilon of the universe as again as maybe just one class. And you know, how big is that epsilon depends on how much you are keeping up in terms of the connections. But these are connections. You know, reading any concept as if it was the only concept in the world, what's the point? You're that stupid. You need to understand how things are connected. Okay? So anyway, that's basically what it is. Anytime you come, prove the correctness of a program, then if the correctness proof doesn't require some of the statements in the program, those statements were not needed. Makes sense? Right? And that's what I did here to increase the, the generality in the ordering. And you can do that in a more general sense to do it for, position constrained plans too. It's the same idea. Any other questions? Any questions? Yes.
I asked this on Piazza, but it's kind of relevant now. So you can have a different type of position constraint where it's like something sick, like I can only do something on a full moon, and that's a little bit different than like I have to start or end by this time.
Yeah, but those are still essentially. Those are still relative constraints. Position constraint means you are pegged to the time. What you are saying is relative constraint. Full moon time and this time are connected. And full moon time may well be happening only in certain times. Right? And that's basically, again, from a representation perspective, simple temporal networks beat anything. I mean, basically, the plan space representations beat anything. Remember the following thing. Why did I prove the correctness of this using plan space? I could have proved it using progression, in which case everything will actually take part in the proof and nothing to remove. Do you understand what I'm saying? It's not a good proof. It's actually, the plan space proof is a beautiful proof because in some sense that's how you think of plans. You never actually look at a big plan and say, let me do the first step, then do the second step, then do the third step, then do the fifth step, and then after the 2000 steps, are the goals true? That's not what you do. You look at, say, is there something in this plan that is actually giving what I need? That's the kind of analysis we do. Do you see what I'm saying? And so, there are proofs and there are proofs. This is the most parsimonious proof of the correctness of the plan. The more parsimonious the proof is, the more generalization you get. They're all, from the theory perspective, they're all correct proofs. One that is correct by this will also be correct by the other thing. But because you use the parsimonious proof, you are essentially able to actually. That's the reason why even if you don't do plan space planning as a search strategy, understanding plan space planning concepts is extremely important. Because most of scheduling, most of temporal planning, everything is connected to plan space. Again, for every topic in the course, there could be the rest of the semester just on this topic, but we will shift to abstraction next class. Have a nice big break. Think about your projects.